PN junction diode. Now, before going for a PN junction, first we'll see how a p-type semiconductor is represented, how an n-type semiconductor is represented. Then we'll go for a p-type PN junction. Take this is a p-type semiconductor. Majority charge carriers are holes. Let us suppose I am representing like this. Minority charge carriers are electrons. Let us suppose these are electrons. These are holes. These are electrons. Now, more positive charge than negative charge. That means this way of representation is wrong. Because either p-type semiconductor or n-type semiconductor, it has to be electrically neutral. So, what is going? How to represent that one? So, this positive charge hole is compensated with a negative ion. Negative ion. Okay. So, here positive charge, negative charge. Okay. Overall, if you take total positive charge is equals to total negative charge. Here if you see these two electrons are having negative charge, don't assume it's a negatively charged. There are two ions we have to reduce. Okay, two ions reduce if two these things are there. Then it is electrically neutral. This is the representation of p-type semiconductor. Coming to an n-type semiconductor, how it is formed, how it is represented. In n-type semiconductor, majority charge carriers are electrons. There are some holes. Once again, it is electrically, is it negative? No. It is compensated with a positive ion, a positive ion, a positive ion. Now, for clarity, I removed two positive ions so that it becomes electrically neutral. So, here total negative charge. Negative charge means electrons and electrons are having negative charge. These ions are having positive charge, holes are having positive charge. So, sum overall total positive charge is equals to total negative charge. Ions plus electrons plus holes combinedly neutral. Coming to metals, nothing but a conductor. What is going to happen? Metals, there are so many number of electrons, there are no concept of holes. In metals, there is no concept of holes. Only semiconductors will have a concept of holes. Now, that means it enter negative charge? No. Each electron is associated with a positive ion. Clear? Now, this is electrically neutral, anything, take it, it is electrically neutral because total positive charge equals to total negative charge. Then one more gate question is, as I think that comes in semiconductor physics only, I have not given that point because with the figure I can able to explain, that's a better way, that's why I have not given. Now see here, as temperature increases, what happens to resistivity or resistance offered by metal? Nothing but a conductor. What happens to resistance offered by the conductor? As temperature increases. Now temperature increase in a metal, temperature increases. more number of electrons will be generated or not? Thermal excitation takes place, so electrons comes out of the valence band, okay, therefore more number, but the area will be same area, already it is contained this many number of electrons, some more electrons are added, what is going to happen? And these free electrons are moving randomly within the same space, the number of electrons are so many large that there one is colliding with another one is colliding, like this collisions, more number of collisions takes place. More number of collisions takes place means nothing but they cannot, what is the expected distance, they are not traveling, okay. Previously this much distance is traveled means as temperature increases, more number of electrons are generated, more what we can say collisions. So it's not traveling freely. From here its collision takes place. So next collision takes place. Previously it can freely move, but now because the charge carriers are increased, the collisions increases, therefore resistance increases. That means conductivity decreases. For a metal, that's once again this is applicable only for metal. For metal, as temperature increases, resistance increases. Number of charge carriers increases. Exactly speaking, current has to increase, but that metal is not going to have. As the temperature increases, resistance increases, conductivity decreases. Whereas in semiconductors, as temperature increases, more number of covalent bonds are broken, the number of electrons and holes are going to increase. But initially there are less number of charge carriers are there. Therefore, having increasing more further, there is no problem because area is available. Initially less number is there. If increase the temperature, number of charge carriers are increases, current increases, resistance decreases, conductivity increases. For semiconductors, as temperature increases, number of charge carriers increases. Okay. Number of charge carriers increases, resistance decreases, conductivity increases, resistance decreases, current increases. Whereas metal, it's opposite. Therefore, it's called semiconductors are having negative temperature coefficient of resistance. That means as temperature increases, resistance decreases. Metals are having positive temperature coefficient of resistance. That means as temperature increases, resistance also increases. One more point. Okay, that's clear? Now comes, okay, this is the representation of p-type semiconductor, this is representation of n-type semiconductor, this is representation of a metal. Now how a p-n junction is formed? How a p-n junction is formed? Take a silicon or germanium. Don't take this is a this is a p-type semiconductor, this is n-type semiconductor, joining like this at center p-n junction. It's not like that. Take a silicon or germanium crystal, one side add p-type impurities, another side add n-type impurities, then a p-n junction is formed. Adding, there are two methods are there, diffusion mechanism, ion implantation. That we will see the last, how to add the impurities to a crystal. Okay, take a silicon crystal or germanium crystal, one side of the semiconductor add p-type impurities, other side add n-type impurities, at the center, at the middle somewhere you will get the p-n junction. Okay, now we are going for how a p-n junction is represented. Okay. Now taken this is a p-type semiconductor. We have taken a silicon crystal or a germanium. One side we have added boron impurities, nothing but acceptor impurities. Other side we have added the phosphorus impurities, nothing but donor impurities. Then it is represented like this. Then it's an imaginary surface which separates the N-type, P-type semiconductor and N-type semiconductor, and I have represented with the dotted lines. It is not, there is no clear-cut boundary. We are assuming it's there because of separation. Now what is going to happen? Once you have added one side P-type impurities, other side N-type impurities you have added. Next step, what is going to happen? See here, here we are having holes, here we are having electrons. Okay, here we'll add some holes also. If you see here, more number of holes here, here less number of holes. So concentration gradient of holes is there or not? Now, so concentration gradient here high, large number of holes, here less number of holes. Therefore, holes will move from here to here. Here more number of electrons, here less number of electrons. That means in this direction concentration gradient is existed. Therefore, electrons will move from high concentration area to low concentration area. Therefore, electrons are moving in this direction. Why these holes and electrons are moving? Are you applying any external field? No. Internally developed concentration gradient. Because of the concentration gradient, there is a movement of charge carriers from high concentration area to low concentration area. That is called diffusion mechanism. Now the starting diffusion is existed. So what is going to happen? This hole moves in this direction, this electron moves in this direction. Hole is having a positive charge, electron is having a negative charge, both will attract with each other and they are coming like this. Therefore, already I said in the previous session, electron hole comes in contact with each other means they will recombine. They will recombine means they will disappear, becomes a valence electron. Valence electrons we are not going to represent it. Okay? Therefore, this electron and this hole is going to disappear, becomes a valence electron. Similarly, this one combines. Clear? Now my first question comes here, important one. This ion is having negative charge, this hole is having a positive charge, this moves in this direction, this moves in this direction, both will recombine and they will disappear. Is it going to happen like that? No. Okay? Why? Ions are immobile. Ions are immobile means they will not move from its position. So nucleus force is there, it's donating or accepting one electron, it becomes ion. It will be in that position, it will not move. Okay? Then who is going to move? Free electrons and holes are mobile charge carriers. Always current is due to mobile charge carriers, not due to immobile ions. Okay, next. Okay, therefore this is not going to happen. So next what is going to happen? Because of diffusion, this electron comes here, this hole and electron comes like this. Therefore, once again, these both will combine, they will disappear. This will combine with this one, this will recombine with this one. Clear? Now, next this will recombine with this one, this will recombine with this one, this one recombines with this one. If all the electrons and all the holes are recombined, so left over is only ions. What is the use of ions? Immobile. There is no use. That means it's not happening. This electron hole will not recombine with this one. That means after certain time, the diffusion will be stopped. Now see, there is a concentration gradient still existed or not? Yes, still concentration gradient is existed, but diffusion will not take place. Why? We'll see. This hole comes to this one freely. But now see here see, negative charge, positive charge, neutral. Negative charge, positive charge, neutral. Positive charge, negative charge, neutral. Positive charge, negative. That means this entire portion is neutral, this entire portion is neutral. But here now previously an electron is there, now it's disappeared. Electron is there, disappeared. Electron is there, disappeared. That means now it becomes, from here to here we are having a positive charge. This positive charge is now sufficient to repel the positive hole. Hole will move freely from here to here, because here say negative charge, it will be attracted towards in this direction. It comes here, but once it comes to nearer to the junction center point, this positive charge is sufficient to that it will repel the positive hole. Now the positive charge due to ions is sufficient to reflect the or oppose the movement of the positive hole. Therefore, there is no further diffusion. Diffusion will be stopped. Okay. Therefore, it will not move. Similarly, it will comes here. This will be what we can say, repels. It will not move further. Is it clear? Clear? That means after certain time, that there is no further movement of the charge carriers. So one side we are having positive charge, other side we. Now what about this portion? Is positive or negative or neutral? What about this portion? Positive or negative or neutral? This portion, see, positive charge, negative charge, neutral. This portion is neutral. So this region is called depletion region. Depletion region. What is meaning of depletion region? What is the meaning of English dictionary meaning of depleted? Depletion means used. Depleted means used. Previously here we are having what we can say hole. Here previously we are having electron. That electron and hole are now not existed. Not existed and previously existed, now they are not existed. That means we have used those electrons and holes. Used means depleted. Therefore that region is called depletion region. Okay, and also called as space charge region. That means this area contains, this region contains a positive charge and negative charge. That area is contains its charges, therefore it's called space charge region. And the width of this one, this is called width of the depletion layer, and it is around 1 micron, 1 into 10 power minus 6 meters. Okay, then this is called width of the depletion layer in p-type semiconductor. This is called width of the depletion layer in n-type semiconductor. Therefore, W equals to width of the depletion layer in the N and width of the depletion, summation of width of the depletion layer in P and N. Now whether WP and WN are similar or not, that we'll see later. Okay, after completing this part we'll go for whether WP and WN are similar or it will depend on some other parameter. We'll see that afterwards. Now that means because of diffusion there is a initial movement of charge carriers taken place or not. That means any current will be resulted. Initially because of diffusion there is a movement of charge carriers. That means holes are moved from here to here, electrons are moved from here to here. That is total current equals to hole current plus electron current. That means some diffusion current is existed initially. No, that is 0. Why? We'll see. Now, here we are having negative charge, here we are having positive charge. Here neutral, this part is neutral, this part is positive, negative charge, positive charge. That means there is internally electric field is established. What is this electric field is doing? Okay, it will allow minority charge carriers. It will allow minority charge carriers. Now, internally developed electric field will allow the minority charge carrier. What are the minority charge carriers? Here it is hole, here it is electron. Now minority carriers are around means current will be existed or not, and it is very small. Previously diffusion current is a small value, now drift current. Now internal electric field is established. Electric field is established because of that internally developed electric field. There is a movement of minority charge carriers. Therefore, current is going to exist. And that current, see, now this is because of diffusion. Because of drift, hole is moving from here to here. Electron is moving from here to here. So this is drift. See, diffusion current and drift current are opposite or not? And the magnitude of drift current and magnitude of diffusion current is equal. Therefore, under unbiased, that means externally we have not applied any external DC voltage. See here, it's left half stage. We have not applied any external DC voltage. This is called unbiased. Under unbiased condition, internally developed electric field will constitute some drift current. Because of diffusion, some current will be existed. Both are in the opposite direction and magnitude will be equal. Therefore, current will be zero initially under unbiased or open circuit condition. Clear that point? Now comes to our next point. Charge density. On y-axis we have taken a charge density rho, or rho, it's better, rho, charge density. Okay. On x-axis you have taken distance. Here it is center. Now from here to here, it's a neutral or not? Neutral means like this. From here, it's a neutral. Clear? Now here we are having what this charge, positive charge, indicate like this. It's a positive charge. Positive charge, and it contains what are these ions? Donor ions. Here we are having negative charge, and this is Ma. So here neutral, here from this portion it is negatively charged, and at the junction it is shift to positive, and here it is neutral. This is called charge density plot. Now this type of PN junction is called abrupt junction. This type of PN junction is called abrupt junction or step graded junction. Step graded junction. Instead of this way of charge density plot, there is a one more plot is there. Here it is neutral, here it will be like this. Okay, once again here it's neutral. From here it's increasing linearly, therefore it's called linear grown junction. Linearly grown junction or linear junction. That type is called abrupt junction or step graded junction. This is called linear junction or grown junction. It's linearly increasing. Once again here it's negative charge, here you will have a positive charge, neutral, neutral. This type of PN junction is called linear junction or grown junction. This type of junction is called abrupt junction or step graded junction. Most of the cases we are using the abrupt junction only, that's why default assume it as a abrupt junction. Now, electric field. I said electric field is existed. If you plot the electric field From here it is neutral, therefore here electric field is 0 because it's a neutral. How to get the electric field? We know charge density. If we integrate the charge density, you will get electric field. E equals to integration of rho, that's nothing but charge density. Therefore, if you integrate this one, okay, if you draw correctly, both will be equal, actually you will get it. Okay. Now, this is called electric field max, E max. One of the gate question is, electric field will be maximum at, okay, option C, given some options. What is electric, where is electric field is maximum? At junction x equals to 0. Then it comes decreasing, it's magnitude only, okay, magnitude of electric field is maximum at junction at x equals to 0. Either any type of semiconductor, that means any type of doping, electric field will be maximum at the junction. Clear? So this one is charge density plot, this is electric field plot. Electric field will be maximum at the x equals to 0. Another gate question is, the depletion layer contains dash. The depletion layer contains dash. Options are electrons, option B, holes, option C, electrons and holes, option D, immobile ions. Okay, answer is immobile ions. Depletion layer contains only immobile ions. That's another gate question. Next gate, another gate, current is due to, in a semiconductor or in a PN junction, current is due to, option A, only due to electrons, option B, only due to holes, option C, only both due to electrons and holes, option D, due to electrons, due to holes, and also due to ions. Answer is, ions are immobile, therefore there is no current due to ions. Either a positive ion, negative ion will not contribute any current. The only electrons and holes. Electrons will contribute current, holes will contribute current, but ions never contribute current. Next, another gate question. All these are asked, okay. W, in this figure, WP and WN are same or different, or it will depend on some other parameter. Okay, that I will explain. If acceptor impurity is equals to donor impurities, that means amount of doping in n-type semiconductor and an amount of doping in p-type semiconductor, equal amount of doping is done for both n-type semiconductor, n side and p side, okay, either side, then WP equals to WN. That means the width of the depletion layer is equal in p-type semiconductor and n-type semiconductor. Now let us assume that Na is greater than Nd. That means more number of acceptor impurities. Then see the depletion layer, how it. This is a p-type semiconductor, this is an n-type semiconductor, take this is center point. We have added more number of acceptor impurities. That means here more number of holes. Then here ions will be there. Neglecting minority carriers. Now, in n-type semiconductor, electrons will be majority carriers, but I have taken the donor impurities are less. less means here we are indicating very few. This is the representation. Here more doping, here less doping. Therefore here positive ion, here positive ion, here positive ion, here positive ion. So once doping is done, what is going to happen? This will recombine, this will recombine, this will recombine. So this will disappear, this will disappear, this will disappear. Assume this much is sufficient for the repulsion. Further there is no movement of charging ions. Assume for simplification. Now this is the depletion layer in p-type semiconductor. This is center. This is the width of the depletion layer in n-type semiconductor. So what is the meaning of this thing? More doping, the width of the depletion layer is less. So the depletion layer will penetrate more into the lightly doped region. In this case, lightly doped region is n-type semiconductor. Therefore, the depletion layer will be more in n-type semiconductor, less in p-type semiconductor. Clear that point? The depletion layer will penetrate more into the lightly doped region. If Na far greater than Nd, then Wn far greater than Wp. Similarly, Nd far greater than Na, Nd far greater than Na, then Wp far greater than Wn. So final conclusion is, if doping is equal for p-type semiconductor and n-type semiconductor, nothing but donor impurities and acceptor impurities are equally added, then the width of the depletion layer in n side and p side is equal. Else the depletion layer will penetrate more into the lightly doped region. More into the lightly doped region. Clear that point? The next one. There is one relation which is required for problems. Wn into Nd is equals to Na into Wp. Wn into Nd, okay, is equals to Na into Wp. See here the same example. Here impurities are added more. Na is more, this is more, therefore automatically Wp is very small. Here Nd is very less, Wn is very large. Overall both are going to be same. Therefore the relation is Wn into Nd is equals to Na into Wp. Then there is one more formula. Electric field maximum value, maximum electric field is equals to E Nd Wn by epsilon. Na, wait one minute. Na means it's Wp. Na Wp by epsilon, or maximum electric field is, this is in terms of Na and Wp, Nd Wn by epsilon. Either this formula or this formula, that depend on the given data. Maximum electric field at the origin, x equals to 0, that's nothing but at the junction, and its value will be given by E Na into W by epsilon or E Nd Wn by epsilon. Okay. Next point. What is epsilon? Permittivity of free for permittivity. Epsilon is permittivity and is given as epsilon r into epsilon naught. Epsilon r is relative permittivity of an dielectric. Epsilon naught is free space permittivity. Epsilon naught is free space permittivity. It's a constant, some value is available, I will quit. Epsilon r is relative permittivity. Clear? Next. Another point. Diffusion current in this PN junction, diffusion current is due to majority carriers or minority charge carriers. Diffusion. Holes are moving from here to here, electrons are moving from here to here. That means majority carriers are moving. That means in a PN junction, majority charge carrier, diffusion current is due to majority charge carriers. Majority charge carriers. Clear? Drift current. Drift current, what it is doing? It is allowing the minority charge carriers. Drift current is due to minority charge carriers. Diffusion current is due to majority charge carriers. Drift current is due to minority charge carriers. Clear? Next. Now, okay, we'll take here. Assume this is the depletion layer. Already I said there is an electric field is internally developed. That electric field is maximum, that we give it. Now it is offering a barrier potential or not? V. Okay? That is called built-in potential or barrier potential. Why it is called barrier? It will not it will oppose the, it is acting as a barrier for the flow of holes from P to N, electrons from N to P. Therefore it's called barrier. And the potential is, it's open circuit under unbiased condition, therefore it's open circuit, unbiased. Okay? It's unbiased condition, it's called barrier potential. And it is given by Vt ln Na Nd by Ni square. What is Na Nd, Ni? Accept impurities, donor impurities, intrinsic concentration. Okay. Now let us suppose this is the width of the depletion layer. We know Wn, Wp, okay. Now what is the formula for W, width of the depletion layer? It is square root of 2E by epsilon into V naught 1 by Na plus 1 by Nd. 2E by epsilon, 2 epsilon by E. 2 epsilon by E into V naught built-in potential or barrier potential into 1 by Na plus 1 by Nd. This is called width of the depletion, total width of the depletion layer. Clear? This is barrier potential. Now, I want only Wn. What is the value of Wn? I want only value of Wp. What is Wp? Okay. Take down this formula. Wn is equals to W into Na by Na plus Nd. This is W into Nd by Na plus Nd. Wp equals to W into Nd by Na plus Nd. Wn equals to W into total width of the depletion layer. Calculated here. Na accept impurities, Nd donor impurities. So all these formula are very important for problems point of view. This one and also this formula, all these are very important. Clear? Next. This PN junction is denoted as it's also called as a diode. Diode means it's a two-terminal diode. This is called anode, this is called cathode. Under unbiased condition, under open circuit condition, current is zero because of the barrier. So what is the use? Current is zero, no use. Therefore what we are going to do is, we are going for biasing. What is meant by biasing? It is an application of external DC voltages. Application of external DC voltages is known as biasing. It is a process of application of external DC voltages is known as biasing. Now, what is the need for biasing? If you apply biasing, then only it is going to work as a some application, in some application. Now, it can be a forward bias, it can be a reverse bias. Two types of biasing, forward bias and reverse bias. Coming to forward bias, if anode is connected at higher potential, not positive terminal, battery negative, okay? If anode is connected at higher potential than the cathode, then the diode is said to be forward bias. If anode is at lower potential than the cathode, then the diode is said to be reverse bias. Example, see here, I'll take this example. Here 5 volts, here 3 volts. Both are positive or not? Therefore anode is at higher potential, anode is at positive terminal, cathode is at negative terminal of the battery, then the diode is said to be, it's not better way of giving the thing, okay, definition. If anode is at higher potential than the cathode, then the diode is said to be forward bias. If anode is at lower potential than the cathode, then the diode is said to be in the reverse bias. Okay. If you apply forward bias, if you apply reverse bias, what is going to happen, that we'll see. Now comes, what is the significance of the symbol? If you see here, this is an arrow mark. What is this arrow mark indicates? Its current direction when the diode is forward bias. The arrow mark indicates current direction when the diode is forward biased. Clear? Once we have added p-type impurities, n-type impurities, then immediately diffusion mechanism and drift mechanism takes place. Okay, this disappears. Okay. This is depletion layer is formed. That means it's acting as a barrier. It will not allow the charge carriers from P to N or N to P, majority charge carriers. Now we apply biasing like this. Now this is anode, this is cathode. Anode is connected a higher potential than the cathode, therefore the diode is forward biased. Clear? Now what is going to happen? Externally you are applying some force, and this is a positive force. So what is going to happen? This is a positive hole, this is a positive potential, higher potential. So indirectly you are supplying an energy to this hole. That means this hole will acquire the energy from the external field. So once the electron acquires the energy from this one, it can able to cross the junction. Now this hole can move freely till this point, but once it comes here, this positive charge will repel the hole. Now it has to overcome the repulsion force, means we have to give the energy. Who is giving the energy? From external field. From external field, if we give sufficient energy, then what is going to happen? These electrons acquire the energy from the external field, they will overcome the barrier repulsion force, nothing but barrier potential. So they cross the junction. Once they cross the junction, these holes are attracted by negative terminal, holes are moving like this, therefore current will be resulted. So as this applied external field goes on increasing, more number of holes will acquire the energy and they can overcome the barrier potential. Indirectly what we are going to say? Internal barrier goes on reducing. That means the width of the barrier is, the width of the depletion layer is decreasing. Width of the depletion layer is decreasing. As more and more increasing, more number of charge carriers are crossing the junction, the width of the depletion layer is decreasing, current is increasing. At certain point of time, all the charge carriers will acquire the sufficient energy, so more number is going to cross the junction. That means current increases exponentially. So up to certain voltage, initially there is a barrier is there. So you start from 0, increasing 0.1, 0.2. Very less number of holes are crossing the junction because they acquired, very less number is acquiring the energy. So current is negligible up to certain point. As further increases, more number of holes, similarly as opposite here, more number of electrons acquire the energy, here they will cross the junction. After certain voltage known as cut-in voltage, current increases exponentially. So below cut-in voltage, current is negligible. Once cut-in voltage is reached, that means internally depletion layer is 0, it became 0. Then the charge carriers can move freely from P to N, that means holes can move freely from P to N, electrons can move freely from N to P, resulting in a very large current. Why very large current comes? Because of the majority charge carriers are crossing the junction. Here from here holes are moving to here, electrons are, large number is available, therefore after cut-in voltage, current increases exponentially. Why it increases exponentially, I will explain in the later session. Why it is not a straight line, why it has to increase exponentially, that we'll see it in the next session. Now right now take it as this one. This is called cut-in voltage. Cut-in voltage for silicon is 0.7 volts. It's 0.3 volts for germanium. You can take it as 0.6 and 0.2. That depends on others. Some textbooks say 0.7, 0.3, 0.6, 0.2. Okay, for problems we'll take it as 0.7, 0.3. Theoretical things will take 0.6, 0.2. Nothing. Okay, small difference. Clear? Now, that's about the forward bias. In forward bias, current increases rapidly or exponentially after cut-in voltage. That means once internal barrier potential becomes 0 because of the applied electric field is opposite to internal electric field. Now what is going to happen? Let us suppose next we apply in this way. That means now previously they are crossing like this. Now what is going to happen? These holes will be attracted. Instead of crossing the junction, they will move away from the junction. Once again holes are coming back to the same position where it's generated. They are not crossing the junction to result a current. They are coming back. Okay, therefore, now what is going to happen? The width of the depletion layer, now charge carriers are moving means the width of the depletion layer increases. The width of the depletion layer further increases. So if you apply a reverse voltage, the width of the depletion increases. Now when you can move from very large required, forward required, you have applied reverse voltage. If you apply reverse voltage, the charge carriers are moving away from the junction, therefore the width of the depletion layer increases. Majority carriers are not crossing the junction. But if you see here, positive charge, negative charge, internally an electric field is there. What is internally electric field will do? It will allow the minority charge carriers. It is allowing the minority charge carriers means, okay, a small minority charge carriers are less in number, therefore it comes like this, and it's a constant, less number of charge carriers and equal number, okay, current will be remains constant. So under reverse bias condition, current is very small and it is called reverse saturation current. What is the meaning of saturated? If 10 electrons are there means for starting only it is due to 10 electrons, always it's continuously only due to 10 electrons. Saturated means there is no further increase in the temperature, further increase in the current. Clear? Once again we'll see these things in the next class. So before going further break, we'll have a continuation with the problems, questions. First question. Okay, clear. Next, yeah, Kirtana. Sir, continuity equation and Hall effect topics are included in GATE. Yes, it's included, that we are going to see later. Yes, it's included. Continuity equation is not there actually. Hall effect is there. That's also one of the important one that at the end we are going to see. Hall effect we are going to see at the end. Srishma from Palakkad, Kerala. Sir, what is the relationship between volt and electron volt? Okay. Now, okay, in all the calculations we have done, final answer was written in electron volt. What do we directly get answer? How do we get answer indirectly? Electron volts. Actually, volt and electron volts are different. Energy is expressed in joules. Normally, in all the applications, the energy is expressed in joules, but in electronics the energy levels are so small that joule is a big quantity. Okay, to overcome the disadvantage, what we are going to do is we are taking 1 into 10 power minus, what we can say, 1 electron, 1.6 into 10 power minus 19 joules we are taking. That means we are multiplying the joule with 1 electron. Therefore it is called 1 electron volt. It's nothing but energy. Instead of expressing in joules, we are expressing in electron volts. Clear? Voltage is different, energy is different. Clear? Indirectly speaking, it's only the difference is 1.6 into 10 power minus 19. Clear, Srishma? So always in our applications it's EV. If it is a voltage, we will get it as V. Else energy means electron volts. Next question, Anchal. How we are add impurities in a semiconductor? That's already I said. I will explain while coming for a VLSI. There are two methods are there. I said ion implantation, diffusion. That we are going to see in depth in VLSI. Next question, Abhishek Paul. Sir, please show the electric field direction acting on the electron and holes in the depletion region. Already I said, electric field will be from positive to negative, the direction. Clear, Abhishek? Now it is on the now what is going to happen? This is minority charge carriers, here it is holes. This is having positive charge, negative charge. This negative charge will attract the hole, therefore it will allow the minority charge carriers. Clear, Abhishek? This is the internally developed electric field, that is the direction. That's why I shown previous case, this figure also. Ketna. Next question. Sir, in conductor only electrons are the charge carriers, but how drift current due to holes exists? In metals, there is no drift current due to holes. There is no holes concept at all. Drift current due to holes and electrons are there in a semiconductor. In metals or in conductors, always only due to electrons. There is no concept of holes. Clear? Next, Piyush Binani. Sir, do barriers is reduced in terms of potential or it reduces in terms of length? Actually, barrier is, it's not increased, it's not reduced, it's not like that. You are giving energy to this electron to overcome the barrier. Indirectly we are assuming it's reducing the potential, but actually what is happening is barrier will be there. Okay, now let us suppose this is barrier, it has to come here. This is not having energy to cross. From external source we are giving energy so that it crosses the junction, it overcomes the barrier. It is having some barrier, that means we are giving energy to this barrier to cross the junction. Okay, barrier will be there, but crossing the junction means how to analysis means we are assuming that barrier is reduced or potential is decreased, but everything is existed there, but we are giving energy to cross the junction. Clear? In tunnel diode, instead of crossing the junction, they pass through the junction, they will go through the junction, that I will explain at the time of tunnel. It's clear, Piyush? Okay, now we will complete the session today, we will continue with the next session, next class.